All right, hello everyone. My name is Peter Knowlton. I am a senior working at the planetarium at Williams College this year. I'm also an astrophysics major here on campus. And thank you all for coming to the STEM Week Planetarium show. I'm really excited to give you guys kind of a little tour of the night sky. In a normal year, of course, we'd be in the actual planetarium on campus. But of course, due to COVID, we can't be all together. I hope that in the future we can be, but instead we're going to be using Zoom and a software called Stellarium. Stellarium is a free to download software. You can look it up online, and this essentially is a planetarium simulator. So you get to see all the stuff that we can see with our planetarium, but just at your fingertips on your computer. And if you'd like to schedule a private show, where we'll give these talks via Stellarium and Zoom as well. Highly recommend you reach out to me at pfk1@williams.edu, and we'd be happy to set something up for you and your friends or your class, your club, or anything. So thank you all. Without further ado, let's get started. All right. So we're starting here looking at the setting sun in what looks like a setting that looks like what Williams will probably look like pretty soon as we begin to near the colder winter months. And as you'll see, if I move time forward just a little bit, the sun sets just south of the true west. The stars come out. So this is because we are now past the autumnal equinox. The sun is getting further and further south in the sky, and so it'll kind of occupy more of the southern, the more go further south, occupy more of the southern sky as we get closer to the winter solstice, when it's at its southernmost path in the night sky. Now, if we look up, you can see the Milky Way very nicely here. Of course, the Milky Way is difficult to see in areas that have a lot of light pollution, but also a lot of kind of material in the air, moisture and humidity and that sort of thing. But luckily, at the planetarium here, we have some kind of cosmic powers. So, excuse me, I'm going to actually get rid of the atmosphere so that we can actually see the sky in its kind of full unobstructed beauty. And I'd also like to get rid of these trees that are kind of blocking our way. I'm actually going to take us to the middle of the ocean. Here we are now, zoom out a little bit. Now we are just kind of adrift in the middle of the ocean, looking up at a atmosphereless sky. So of course, something we could never experience in real life, but something that we're able to do in this planetarium. Now, the reason that I am a astrophysics major is because I think there's a lot of significance in studying the stars that relate not just to the scientific, but also to the human experience. So why is this? Well, I think this is a threefold answer. The first is that astronomy is very practical. Humans are incredibly good at pattern recognition. It's something that really defines us against other species in the animal kingdom. And we're so good at it that we would use the night sky to kind of be our first clock. We would use it for time-telling purposes, and we use it to predict seasons. So we would know when it was time to hunt, when it was time to move with a herd of animals, when the rainy season was coming, when the winter was coming, when it was time to move to a new location. We could use the night sky as a very easy to follow constant clock. Move time forward a little faster so you can actually get the impression of the moving sky, and some there's also some satellites and meteors going by. The other thing is that it's artistic. Humans are so good at pattern recognition that we do something that's called false pattern recognition. It's when we see shapes in the night sky that aren't really there. Many of the stars that we see, that we group into these things called constellations, are actually not related at all. But for time immemorial, humans have used these shapes to tell amazing stories, and stories of our gods, of animals, of heroes, and villains, figures of our mythologies. And And for so long, the night sky was kind of this visualization of our own history for each group around all these groups of humans around the world. And it really kind of connected all of humanity, because there were only two skies you could see, the northern hemisphere, the southern hemisphere. So the Greeks saw the same stars as the indigenous Cree, who saw the same stars as the ancient Chinese. There are all these patterns that are common among all these different cultures. And finally, studying astronomy is a bit existential. And this kind of gets at both. I think that, humanity would look up and they tell stories of these figures in the night sky, typically to find out, their origins, where did we come from, what gods created us, is it that god figure over there, is it this group of stars here? But we do that in modern astronomy too. We look up and we try to answer the questions of who we are and what is our place in the universe. We try to understand, the formation of galaxies and planetary systems and the birth of stars and their ultimate deaths, and all the way to the birth of the universe itself. So we're still asking the same questions. We use different tools to answer them, but it's largely we still have these existential thoughts whenever we look up at the night sky. Now, if we were in the planetarium, I'd have a button called Fixed Stars, and that would be what would actually turn on all these stars. But the stars aren't really fixed. Over a long period of time, the stars in the night sky actually will change. On a human time scale, this has not really happened all that much. For about 200,000 years since the human species has been around, the night sky has looked largely how it does now. But over a long period of time, there are three things that happen. First of all, the stars in the night sky move, just like the planets move around the sun. All of our stars are orbiting the galactic center of the Milky Way, and they will drift over time by gravitational interactions with other stars and celestial bodies. And over time, they will move. So if we went back, say, to the age of the dinosaurs, we'd see many of the same stars you see here, but they would be in positions that are totally unrecognizable. Also, stars are not immortal. We think of these stars as these fixed points in the sky that are always there, but stars are born and stars die. They are born from these huge coalescing clouds of rich gas and dust. And then when they get hot enough and dense enough, they will actually begin to fuse hydrogen into helium, creating an internal engine. This engine fuels thermal pressure that pushes outwards. And this fights against the force of gravity that's pushing inwards. But of course, and this is kind of the whole life of the star, is this internal fight between thermal pressure and gravity. But gravity doesn't need any fuel to run. This internal engine creating the thermal pressure does. So stars die when they run out of the fuel, which is hydrogen, for this internal engine, and fusion can no longer occur. And so at this point, the force needed to withstand the huge force of gravity is gone. And so in an instant, the star will actually collapse on itself and then bounce out. The layers will fall in and bounce. And the heaviest stars die in the most spectacular releases of energy called supernovae. These are super, super bright. In fact, they're brighter than entire galaxies. And a number of these have actually occurred in the age of humanity. And I'd actually like to show you a quick example. Excuse me. That work? Cool. I'll pause my music here. So I don't know if any of you guys have seen the show Sherlock. It's a really, really cool show, kind of a modern telling of the classic Sherlock Holmes tales. But this is an example of a fictional example of a supernovae that occurred during human time, like in the human time scale, very recently. And it helps Sherlock solve a crime here.
Painting is a fake. It's a fake. That's why Woodbridge and Cairns were killed. Oh, come on, it's just a detail. The painting is a fake. I've solved it. I figured it out. It's a fake. That's the answer. That's why they were killed. Okay, I'll prove it. Give me time. Will you give me time?
Can.
It's a kid. Oh,
Oh, God, it's a kid. What did he say?
10.
9.
He's giving me 10.
Jesus.
It's a fake. How can I prove it? How?
8.
This kid will die. Tell me why the painting is a fake. Tell me!
7.
No, shut up. Don't say anything. Only works if I figure it out. Must be staring in the face.
6.
Moving you, but how?
5.
Speed it up, Charles.
Oh, the planetarium, you heard it too. Oh, that is brilliant. That is gorgeous.
3.
What's brilliant? What is?
Beautiful. Wonders.
2.
The Van Buren Supernova.
Please, somebody's there. Somebody help me.
There you go. Go find out where he is and pick him up. Van Buren Supernova, so called. Exploding star only appeared in the sky in 1858.
So how could it have been painted in the 1640s?
Right. So essentially what Sherlock did is he recognized that the supernova, which actually, you couldn't see when the star was alive. You could only see it once the star had died and released all its energy. The paint, it only occurred in the 1800s. So the painting couldn't have been painted in the 1600s if this supernova were appearing there. So that's, of course, a fictional example. There's no Van Buren supernova, but there is an example from the year 1054. Just in case, you ever need this to solve a crime, this shows the planetarium is, you can come to the planetarium to learn some crime solving techniques. So we see these supernovae occur when they occur when it's happening in our own galaxy, because they are so bright. So in 1054, there was what was called a guest star, and it was noticed by Chinese astronomers. And this guest star here lasted for about 600 days. The residual light of the explosion. We can see here. This is the Chinese zodiac. Chinese constellations, but we have here Orion. So we can place this in the night sky. But we can't. And of course, after 600 days, the blast eventually faded. It was so bright it was visible even during the day. But once it faded, we can no longer see the energy, the light of this blast, but we can still see the remnants. And it is the very, very gorgeous Crab Nebula. I highly recommend you look at some pictures of this. We have one right here, but there's amazing pictures of the Crab Nebula. And in the center here is the what's left over of the dead star. It is a neutron star. Essentially, it is think of it as the corpse of the old star, and this is all the residual gas and dust and material that was expelled during the explosion. But the star didn't really explode in the year 1054, and this is the third reason that the night sky is not fixed. And this is because light takes time. Light takes time to travel, and light is how we interpret information. So what do I mean by this? Well, we think of the speed of light as this infinite sort of speed, and it is super fast, but it's not infinite. If I were to stand on a big mountain nearby, and you were to stand on another big mountain not too far away, a couple miles away, and I had a super powerful flashlight, and I shined it on you, it would appear to arrive almost instantaneously, but that's just because it is so fast. The moon is 1 light second away from the Earth. So it actually takes light 1 second to get from the Earth to the moon, from the moon to the Earth. So when you're looking at the full moon, you're not seeing the moon as it is right now. You're seeing as it was actually 1 second ago, because the light is how we process information. To give another example, the sun is 8 light minutes away. So when you look at the sun, which you should never do, of course, that proper eye protection, you're actually seeing the sun as it was 8 minutes ago. And the closest star to us, Alpha Centauri, is 4 light years away from us. So that means it takes 4 years for light from Alpha Centauri to reach our eyes. So if there were an alien species living on a planet around Alpha Centauri, and they shined a super powerful magic telescope on us, the light that they're receiving, they wouldn't be seeing the year 2021. They'd actually be seeing the year 2017, because that light from 4 years ago has only just reached their eyes. Conversely, the Crab Nebula is 6,500 light years from Earth. So the explosion actually occurred in the year 5500 BC. This is when, if you're keeping a timeline, cheese was first being made in Poland. Just a fun fact about 5500 BC. So it took 6,500 years for that light to finally reach us and for it to be observed by the Chinese astronomers in 1054. But of course, the explosion actually happened in 5500 BC. Ask another question that relates to this. Do you believe in ghosts? Well, I think you should, at least stellar ghosts. And the reason I say this is because many of the stars we see in the night sky actually died a long time ago. But the light of their death, the explosion, the supernova, has not reached us yet. Now, this may sound morbid, but just as there are many stars who've died, whose deaths we can't see yet, there are many stars who've probably been born, whose births we haven't seen yet, that initial flash that happens when they start their internal engine. We just haven't seen that light reach us yet. So if we were to come back, time travel in the future, 1,000 years or a million years, or we'd probably see a number of stars. Stars we're familiar with have long gone, but there'll probably be a number of stars too who we're not familiar with yet, and we'll get to know. So it's stars. It's kind of fun to anthropomorphize these stars and just to imagine them as having these births and deaths and everything. Now, I've said that this night sky is fixed, and that is for the most part on human time scale. That's the case. Many of these small events are pretty rare, like the supernova and everything. But there is one thing that has changed over the course of human history, and that's the North Star. So the Earth rotates on a tilted axis compared to the ecliptic plane here. So the ecliptic plane here is where all the planets and orbit the sun. And this would be perpendicular to the ecliptic, but we actually orbit about this, kind of like a top. Now, this is actually why we have the seasons. Because the Earth is tilted, at certain times of the year, the northern hemisphere is getting more direct sunlight than the southern hemisphere. So it is summer in the north and winter in the south. And the opposite is true when the southern hemisphere is tilted towards the sun. It is summer in the southern hemisphere and winter in the northern hemisphere. Now, the Earth rotates on this axis, kind of like this spinning top here. And I'll send it away now because it's a little distracting. But as you can see, that handle at top, as it was spinning on its tilted axis, it was doing this. And it was changing the direction it was pointing in at this whatever ceiling the top was in a periodic cycle. And this is called precession. So as long as that top is doing that, until it eventually falls, that this process is called the precession of the axis of the top. So the Earth's axis actually has the same periodic cycle. The top, it happens because the top is being acted upon by other forces, mainly gravity and friction of the table. The Earth is also being acted upon by other forces, the moon mostly, and then the sun, and to a lesser degree the other planets. Because of this, it goes through the same precessional cycle. Now, for the top, that's happening about like a second. It takes for it to go from here then back to here. For the Earth, this process takes 26,000 years. So, to give you an idea of how this actually affects the North Star, well, the northern axis of the Earth is right now pointing close to Polaris, not exactly at it, but very close. And so when as the Earth rotates on its axis, all the other stars appear to go around Polaris. But over time, where our north axis is pointing as changes over this 26,000 year period. So in about 12,000 BC, Vega, this star here, was our most ideal North Star. This is when dogs are being first domesticated about. Then in about 3000 to 1000 BC, this star here called Thuban was our North Star. This is around when writing was first being created in ancient Sumeria. And it was also, it's believed that the pyramids of Giza were built with Thuban being the reference to the North Pole, to the North Star. Then furthermore, after a little bit, there was not a great North Star for a little while. And then finally, in about the year 500 BC till now, Polaris has been the North Star. And this is most credited to the Phoenician astronomer and philosopher Thales of Miletus. He was Phoenician. The Phoenicians were a group from the modern day Levant, and they were expert sailors, and they used the North Star to as their northern reference, which helped in their navigation around the Mediterranean. And they eventually taught the Greeks to do the same. Polaris was actually initially used to be called Phonis by the Greeks because of its association with the Phoenicians. It was only named Polaris in medieval times because Polaris is kind of a new Latin word for pole star. And as I said, we're moving constantly in this arc, and we'll actually reach this point here where we're closest to the north, to true, where Polaris is closest to our true north in the year 2100. So really not that far away. Then over time, of course, we will, after that year, we will slowly move further and further away from Polaris, at which point we will get in around the year 4000 AD. We will get this star here called Orion. That'll be a better North Star. Then in the year 7500 AD, we'll get Alderaan, this star here. Then like around 10,000 AD, we'll get Deneb. And then finally in 14,000 AD, we'll have completed that 26,000 year cycle, and Vega will once again be the ideal North Star. But for the most part, for the rest of our lives, Polaris will serve as a good North Star. And the best part about Polaris is actually a super easy star to find. That's why it was so often used for navigation, because you could find it really easily using the Big Dipper. Of course, the Polaris is called Ursa Minor or the Little Dipper, but the Big Dipper, which is this group of stars here, you could use these two pointer stars here. This is Merak and Dubhe. Oops. Merak and Dubhe. And taking the length of these two stars, if you go in this direction, and you take this length, and you go make about 5 of this length in this direction, and eventually you will reach Polaris. And it was so easy to find the Big Dipper. It was one of the most prominent constellations in the night sky. So for that reason, Polaris while it's not the brightest of stars, was a very good North Star, being so easy to find. Now I want to talk a little about the Big Dipper and Ursa Major. Because it's such a prominent group of these 7 stars are so prominent, humans have looked to the Big Dipper for millennia. And it's believed that the earliest stories of the Ursa Major and the Big Dipper go back to the Paleolithic era. And it's based around this story of the hunt of a great herbivore. Perhaps this story was made the last time the Polaris was a North Star, those 26,000 years ago, when we were at that point in our cycle of the precessions. And we still actually, this story of the hunt of a great herbivore, it can still be found in cultures throughout the world. We still use this story in the Greek mythology. It's the story of Callisto and Arctus. And I'll tell this story really quickly. So Callisto was a nymph and a member of Artemis's hunting party. She was also the daughter of King Lycaon, the king of Arcadia. Then one day, the king of the gods, Zeus, saw her from atop Mount Olympus, and he was immediately enamored by her. And he came down disguised as one of the other huntresses of Artemis and assaulted her. Then, in order to hide his crime from his wife Hera, he turned Callisto into a bear, hoping that that the bear would just wander the woods and Hera would never be none the wiser. While she was a bear, she gave birth to her and Zeus's son, who was named Arctus. Now, Arctus actually comes from the Greek word for bear, and it's where we get the word Arctic, because the Ursa Major and Ursa Minor, the big and little bear, are found in the northern sky, the Arctic sky. So that's a little fun fact for you all. Zeus had Hermes hide Arctus with King Lycaon, Callisto's father. Now, King Lycaon was plagued with this thing in Greek mythology called hubris. He believed that he could test the omnipotence of the gods with his grandson Arctus. Hubris is this belief that you. It's this pride. You're better than everyone else. And so one day he wanted to test Zeus's omnipotence. So he invited Zeus to a banquet, and the food that he served at the banquet was actually his own grandson, Arctus. He found Arctus and essentially cut him up and turned him into hamburger meat. And his idea was that if Zeus was truly omnipotent, he truly knew everything, then he would know that what he was eating was Zeus's son, let alone Lycaon's own grandson. Now, of course, Zeus is truly omnipotent, and so he immediately knew that this was Arctus, and he was furious. He destroyed King Lycaon's castle, and he turned King Lycaon into a wolf. And this is actually where we get the word lycanthropy, to become a werewolf. Lycaon was the first werewolf in Greek mythology. So Lycaon ran off into the woods, and Zeus actually put Arctus back together and gave him new life, and Arctus became the new king of Arcadia, which later was named after him. And he became a really well-loved ruler and an even greater hunter. And you might see where this story is going. One day he was out on a hunt, and he came across this huge bear, which he turns out was his mother, Callisto. And Arctus was overjoyed. Sorry, Callisto was overjoyed to see her son. She recognized him immediately. But Arctus did not recognize his mother. He just saw this big bear charging after him. And so he raised his arrow to kill her. But Zeus decided he wanted to stop the bloodshed. And he just arrived down, he came down to earth, grabbed the arrow out of the air, and he turned Arctus into a bear as well. And you can probably see in this art that Ursa Major has this really long tail. I don't know if you guys have ever seen a bear before, but they've got pretty short, stubby tails. But they're always depicted this way. And this is because that Zeus grabbed Ursa Major, Ursa Minor by their tails, and kind of in that Olympic event, that Greek, where you spin around the ball and chain, he spun them around and elongated their tails in the process and threw them into the night sky, where they exist to this day. So now, of course, they are the two of them are kind of dancing around each other around the North Star, which exists at the end of the tail of the little bear, Ursa Minor, which is Arctus. Now, I was saying earlier how the story of this hunt of an herbivore goes back to the Paleolithic era. And so it actually predates the crossing of the Bering Strait. And so this story of the Big Dipper can be found. The story of this great herbivore hunt of a great herbivore can be found all over the world, because it's all traced back to this original story before humans began to spread out. And so the hunt of the bear, which we see in the Greek story, is also a scene in the indigenous Cree story, where the indigenous Cree see the Big Dipper as a bear. These two cultures that had no connection to each other, the Greeks and the Cree, shared this story from a common ancestral story from thousands and thousands of years before them. And I'd love to tell you guys that story right now. Well, this is the scene of Arctus making ready to kill his mother, and Zeus coming down to aid them, to help the two of them in the situation. So we have on kind of in the blue there is the Greek stars, and overlaid are the indigenous Cree stars. And here we have this bear right here, a little zoomed in, and we see the Big Dipper here, and this is Mista Musqua. Mista Musqua was this gigantic cave bear who terrorized the North American continent. He would go around tearing up crops, destroying homes, and scaring away everyone who got in his way. So finally, one day, the animals decided they had enough, and they all got together to have a meeting. And the idea was the purpose of this meeting was to figure out what to do with Mista Musqua. Now, many of the animals talked about how they tried to reason with the bear, but the bear just wouldn't see reason. The bear just wanted to cause destruction and mayhem wherever he went. So it was decided, okay, the only thing we can do to deal with this bear is to actually drive him away from the land. And no animal was brave enough to stand up to Mista Musqua, except for 7 birds. And these were the 7 hunters. They were a chickadee, a gray jay, a pigeon, a blue jay, a horned owl, and a saw-whet owl. And they were all led by a robin named Pipichu. Pipichu and the 7 birds and the 7 hunters made ready to go out and drive away Mista Musqua. But there was one group of animals who really liked kind of the current status quo, and they liked following Mista Musqua around and just eating his leftovers. These were the ravens. The ravens were leading a pretty good life with Mista Musqua if they just stayed out of his way. And so the ravens actually flew out to warn Mista Musqua of the 7 hunters coming to get him. And of course, Mr. Musco was furious. He's, how dare these birds dare to defy me? And so he went out to go meet the birds himself. And eventually the two groups met. The confrontation began. Mr. Musco got up on his hind legs and tried to scare away the seven hunters. But of course he couldn't. These birds would not be, had a great resolve and would not be moved by mere intimidation. Mr. Musco, at the end of the day, is just a big bully. He was all bark and no bite. He would not actually, he was too scared of these birds to actually stand up against them. And as all bullies do, when they're met with some resistance, he ran. And he ran away. He sprinted away, trying to get away from these birds, and the birds chased after him. And the chase got faster and faster and faster. It kept getting so fast that it eventually got so fast they actually started to rise up into the sky. And as they were rising into the night sky, Pipichu the robin landed a fatal blow on Mr. Musqua. And the blood from the wound actually fell down to earth and landed on the broad-faced leaves of deciduous trees. And that's why we get autumn. That's why we have this, the beautiful autumn here in Williamstown. It is the blood from represented by the blood from Mr. Musqua's wound. And one drop actually landed on the robin's breast, which is why robins have red breasts to this day, as a reminder of the great service they did in driving away and killing Mr. Musqua. Eventually, Mr. Musqua, they went up all the way in the night sky, where Mr. Musqua became the what we call Ursa Major, and the seven birds are actually here. The seven birds are the seven bright stars of the constellation we call Corona Borealis, the Northern Crown. And Pipichu, having landed the blow on Mr. Musqua, is the brightest star, called Alphecca. We call it Alphecca. And to this day, actually, you can see, if you look up the night sky and you see that the Corona Borealis is actually following Ursa Major as the sky moves. So it still looks like the birds, the 700s, are chasing Mr. Musqua to this day. Now, of course, there were some objects in the night sky that didn't appear fixed. We were talking a lot about fixed stars and how they make these constellations, but there were some objects that did move against the background stars. And the Greeks called them wanderers. In Greek, it's planetae. And that is how we get the word planets. And what's interesting is that the planets appear to revolve around us. Now, this is not a crazy idea. In fact, the ancients tried to test this actually with something called parallax, where if you hold out your thumb and you open one eye and close the other, you'll see that your thumb moves against the background image. I can't really show you here on Zoom, but you'll see your thumb will kind of move against, depending on which eye you're looking at. And so the idea was that if the Earth's going around the sun, then if we take a look at the stars in January and look at them in June, then the background star should have shifted a bit, much like our thumb. And the further the stars are, the less they move. Whereas if they're closer, they move a lot more against the background. And the fact is they do. We do see this parallax in the stars, but it is so small because the stars are so far away that when the ancients saw it, they didn't see any movement. Their instruments were not sensitive enough like the ones we have today. And so they concluded that, well, we must be stationary. Everything must be moving around us. So this whole notion that everything's going around us, while we know it's false today, is not a crazy idea when you think about the instruments and the tests that were done back in the day. This is most often called the geocentric model. And is most often credited to Aristotle, the Greek philosopher. Of course, he did not come up with it, but he kind of refined it for Western audiences and the Greeks and Romans and later successors in Europe. And one of the defining features of Aristotle's theory is that the idea of circular orbits. Everything, all the planets and the sun and the moon and background stars are moving in these perfect circles around us. And this would be kind of a difficult thing as people tried to understand what they were actually seeing and observing with the model that Aristotle had laid out. And one of these concepts that makes it difficult is called retrograde motion. You've probably heard of it. Essentially, it's most often heard about with Mercury, Venus, and Mars. Essentially what you'll see is that the planets will be moving along the orbit. This is the planet Mars being taken, its orbit being like a snapshot of its orbit being taken every night. And it'll be moving along its orbit, and then suddenly it'll change directions and then go back. So if everything's moving in perfect circles around us, how could how is this retrograde motion happening? What could be causing this? Because in the circular model, they don't suddenly change direction and go backwards. So how do we solve this problem, retrograde motion? Well, the Greco-Egyptian astronomer Ptolemy introduced this idea called an epicycle. So essentially, Ptolemy's idea was, here we have the Earth, here we have a planet going around in circular orbit, but the planet is not just going on this line, it's also going in a smaller circular orbit whose center is on the larger circular orbit that Aristotle created. And we see here the background stars, and we see this line of sight that's created with the epicycle, with this retrograde motion. And this sort of made sense. He was really trying to reconcile retrograde motion with Aristotle's model. But as you can see, here's where we throw in all of the lines of the epicycles. You can see things are getting complicated. How could the universe be so strange? Well, this seems to make no sense. So there were a number of other astronomers who later tried to explain retrograde motion. There was the Persian astronomer here from the 10th century, Al-Siji. He was the one who created an astrolabe where the movement of the heavens was because the Earth rotates, not because in Aristotle's model, the outer ring are the heavens, and they're moving around in a circular, around us like all the other planets and sun and moon and everything. Al-Siji created this idea where everything is moving, the stars are moving around us because the Earth is rotating. This still put the Earth at the center, but it was a step in the right direction for why we actually see movement in the night sky. Then there was the 13th century Persian astronomer named Al-Tuzi, and he didn't like Ptolemy's epicycle. He thought it made no sense, so he tried to solve it with what was called the Tuzi couple. And essentially, you would have the planet on this part of the smaller circle, and causes it to seem to move across this line back and forth on the larger circle. As you can see, things are getting complicated. But to give Al-Tuzi some credit, this is a very, the Tuzi couple is still an important part of mathematics. He was also coming up with this idea while he was constantly fleeing from attacking Genghis Khan. The Mongols were invading Persia at the time. And so he had to keep moving around as he was creating this idea while fleeing the invading Genghis Khan. So as you can see, things are getting complicated. Finally, in the 16th century, there was a Polish astronomer named Copernicus. And he was the one who brought the idea of heliocentrism to Renaissance Europe. He was not the first one to come up with the idea, but he brought it to Europe. Heliocentrism is essentially how we understand the universe, the solar system now. The sun is at the center. And this simplified things. This got rid of the idea of the, here we go here. It's got rid of the idea of the Tuzi couple and the epicycle and everything, but it didn't explain everything. Mostly because Copernicus kept the idea of circular orbits. Everything's moving in a perfect circle. And so his ideas were largely ignored at the time because he couldn't prove it. Even though this kind of solved retrograde motion, which we'll explain in a little bit, didn't solve for the apparent change, some other observations in these planets as they go around us. So he was largely ignored because he couldn't prove his heliocentric theory was right. Then came in the Danish nobleman and astronomer Tycho Brahe from the 16th century. He was a very eccentric astronomer. He actually lost his nose in a duel, so he had a brass nose for most of his life. And he just had a lot of time on his hands. So he took numerous observations of the orbits of the planets. But he actually died before he could use any of them. So his apprentice, Johannes Kepler, in the early 17th century, a German astronomer, he actually took Tycho's observations and he used them to give credibility to heliocentrism. And he solved retrograde motion very simply with these observations. And he developed 3 laws that are still the foundations of modern astronomy. And the first says that orbits are elliptical, not circles. Essentially, orbits, this is not to scale, of course, but orbits are kind of these ovals. where when the planets approach the part of the oval that's closest to the sun, they actually speed up. And this definition, this new rule that these orbits are not circular or elliptical solve for kind of the seeming changing of speeds of seen in these orbits of these planets. They didn't make sense in the circular orbit. Why would they suddenly change speeds? So this solved for that issue. And I'd like to show you guys kind of an explanation. I think this video here does a really good job explaining what retrograde motion is and how the heliocentric model and the laws laid out by Kepler actually finally solved for what we were seeing.
So let's start with the basic layout of the solar system. The planets closest to the sun move faster and the outer planets move slower, but they all go in the same direction. Apparent retrograde motion is when the planets appear to temporarily change the direction of their orbit. They don't change direction, it just looks that way from Earth. It's an illusion that unfolds over a matter of weeks or months. In this image, Mars was photographed every 5 to 7 days between October 2011 and July 2012. Once all the photos were combined by aligning the stars in the background, it appears as though Mars looped back on itself before continuing on its orbit. A retrograde illusion like this happens when we lap an outer planet like we do with Mars every 2 years, or when an inner planet laps Earth like Mercury does every 4 months or so. But for both Mercury and Venus, the illusion is hard to actually capture, since they're located on Earth's day side, not on our night side. When those planets are visible, it's only right around sunset and sunrise. But assuming you could see it, here's a diagram of how the Mercury retrograde illusion would work. This line shows our view of Mercury against the background stars. As Mercury passes us by, our line of sight shifts so that for about 3 weeks, Mercury will appear to loop back on itself when viewed from Earth. It's simply a function of two objects orbiting in the same direction at different speeds. If you stood on Mercury, you would see Earth make an apparent loop too.
Yeah, so that essentially explains it explains the retrograde of Mercury very well. It's when Mercury, which is moving faster than us in its orbit as defined by Kepler, when it laps us, it appears to change direction because it's actually in that other kind of that point of its orbit where it is seemingly moving in another direction, but it's just at the other end of its orbit. Mars, the narrator described there that if you're on Mercury, you would see Earth going retrograde as well. And that's actually why we see Mars going retrograde, because we are closer to the sun than Mars. And because of that, we're moving faster than Mars. And so when we lap Mars in our orbit, that's when we see Mars going retrograde motion. And you can imagine this kind of, if you're having trouble picturing this, essentially imagine that you're in a race. You're on a racetrack, cars, horses, whatever you want. And you're in the inner lane, and you're moving faster than another racer in a lane that's further out than you. As you're passing this racer, you know that you're both moving forwards because you can see you and the other racer moving forward against the background viewers and stands and trees and everything. So now I want you to still imagine that as you're passing, imagine you passing this other racer, and now get rid of the stands, get rid of the ground, get rid of the trees and everything. And just so you can only see the mountains super far in the distance, but so far that you have no idea if you're moving, how you're moving against them. They're so far away, kind of like the stars. Now when you look over at the racer that you're passing, the racer doesn't appear to be moving forwards anymore because you have no way to tell how you guys are moving against the background hills and everything. As you're passing, lapping this other racer, they appear to be moving backwards because you're going faster than them. And that's why we see Mars going retrograde motion when we are lapping Mars in our orbit, because then we get to a point then later in orbit where we are far enough that Mars then resumes its kind of forward track compared to the background stars or hills in our case, and it appears to be moving forward again. Just gonna play again. Yeah, so exactly as seen here. Here's Mars retrograde. As we're lapping Mars, we see Mars go backwards for a bit and then resume its forward orbit as we're moving further along in our own orbit. Now, speaking of Mars, I'd like to talk to you guys a little bit about Mars and the history of its exploration. Mars is a particularly exciting planet because it hosts the possibility for life. more so really than any other object we've studied so far in our solar system, and one that we can actually feasibly visit with complex and probes that can take data. So here we have these what look like ancient riverbeds. And these riverbeds support the idea that Mars was once covered in the liquid water needed for life. It would have looked something like this, maybe. An ancient Mars covered in huge oceans and lakes and rivers. Mars exists at this little point within the Goldilocks zone. So the Goldilocks zone is also called the habitable zone. Essentially, it's where water is not too hot, where it'll evaporate, and not too cold, where it'll freeze, like the Goldilocks story. Earth exists very comfortably in this zone. Mars kind of exists on the edge, and by some definitions of the habitable zone, it actually doesn't exist within it at all. But Mars is often kind of placed right at the edge of the habitable zone. However, what happened to all this water then? Well, Mars has since lost all its water, most of which is now had taken the form of ice in the north and south pole of Mars. The belief is that Mars lost most of its water because it has a very weak magnetic field, so it could not hold in as conditions in the solar system changed, and Mars is no longer a suitable place for liquid water to exist. It couldn't hold on to it like the Earth can with the Earth's very strong magnetic field. So it lost it. The belief is that it lost it all into space. Now we've spent a lot of time in the past couple decades sending probes to Mars to look for the possibilities of this potential liquid past and potential former life or life still there, existing in the pockets of water that still exist mostly as ice or underwater caverns, or underground caverns of water, excuse me. So, excuse me. So NASA has sent up a lot of probes to Mars just to study the possibility of life. The first two were Viking 1 and Viking 2, sent up in 1976. And the purpose of these objects was to take photos of the surface and look for any signs of life. Then there was the Pathfinder and Little Sojourner rover, sent up in 1997. This was really just to test if a rover could work on Mars. And it also revealed that Mars was once warm and did indeed once have water. Then there were my personal favorites, Spirit and Opportunity. In 2004, the twin rovers. I remember watching these guys go up back in 2004. I was 6 at the time, but I saw the specials on Nova and seeing what they had uncovered. These were the first big rovers to land on Mars. And while Sojourner only moved a couple of meters, these rovers traveled for miles. And they used very specialized tools to dig into rocks. And once they dug into these rocks, they showed us that Mars was once covered in a water that could have supported microscopic life. So not just that it was wet and warm, it did have actual water that could support life. Then there was the Phoenix lander in 2008. This landed further north than any other a rover or lander before it, to study the ice in the North Pole of Mars. Then there was the Curiosity rover in 2012. The Curiosity's job was to search rocks for clear signs that Mars once had an environment that could support microscopic life in its past. So particularly searching for specific chemical signatures that were giveaways of organic life. And then, as a couple months ago now, we have the Perseverance rover and the little Ingenuity helicopter as well. So Perseverance has a lot of really cool and complex tools that allow it to search for signs of life on Mars now. The first is called on the robotic arm here are called Sherlock and Pixel, fitting what we watched the Sherlock video a little earlier. And the role of Sherlock and Pixel are to identify the materials in the rocks to see if they are signs of life or not, some of these chemical signatures for signs of life. And then on the head of the rover, we have the Super Cam and the Mast Cam Z. And these roles not only give us these cameras not only give us the incredible pictures of the surface of Mars that we've come so used to with all these rovers, but also determine which rocks we should actually study, because it does take a lot of energy and effort to move this rover and to operate it. So we want to make sure that we're studying rocks that are worthwhile, not just any random rock. So these cameras really to help us identify those rocks that we want to look at. Then there is the MOXIE. MOXIE is really an experiment to see whether we can actually turn the toxic Martian air into breathable oxygen, so that one day maybe humans can go to Mars and for long periods of time. And that, of course, that is the hope that one day humans will be able to travel to Mars. It's a long journey and everything, but hopefully once we get there, we set up a base, then we can actually perform longer experiments on Mars and more effective searches for life than we can do remote controlling these rovers. So hopefully MOXIE produces some really cool results. We'll see. So with that, stop sharing my screen. Thank you all for coming to the STEM Week Planetarium show. I hope you all are enjoying your STEM week, and thank you for taking the time to listen to this planetarium show. Again, we really wish we were in the planetarium with you all in person on campus. We hope one day we'll be back there. But what's nice, of course, about this digital platform is I can show you guys things that I wouldn't be able to show normally. So I was able to put together this whole slideshow to show you guys images and really give you guys a really good visual aids to some of the things I would be describing normally in the planetarium, but that I couldn't show as effectively. So there are pros and cons, of course, to all of this. So thank you all for coming. I hope you all learned something. I hope you all enjoyed my talk. If you want to email me about setting a private show at some point, we'll do the same virtual platform. Again, it's pfk1@williams.edu. You can also visit the Milham Planetarium website if you want to find my email there. So thank you all. I hope you have a great STEM week, and I'll see you in the planetarium real soon. Bye-bye.